Okay, well, thanks for inviting me, and it's a pleasure to be back here after quite a few years. Dick and I used to work together fairly often, but it sort of lapsed in the last 15 years, or 20 years. Anyway, so I'm going to talk about, unfortunately, nothing about real astrophysics. It's all about evaporating black holes, the information problem, and things like this. So I'm sure you've all heard of the Hawking radiation. So there's black holes radiate like a black body. Temperature, so MP is the Planck constant. MP squared is h bar, and this is a unit G equals C equal 1. And it's proportional to the surface gravity, kappa, which is one for Schwarzschild. And the luminosity then goes as the Planck's constant over mass squared, roughly, with a fairly small coefficient, actually. All right, so now one issue that immediately I'll just start off by mentioning is that Hawking radiation is often described as being due to pericreation within sort of a Planck length of the horizon in some sense, or tunneling, there's a particle just inside the horizon has a net negative energy because its gravitational potential energy exceeds its rest mass, while one just outside the horizon has a net positive energy. Now, I don't like this very much, and calculations of the semi-classical stress energy tensor, which describes the Hawking radiation and other aspects of the energy momentum tensor around a black hole, in the first order in h bar for a classical background. And so these calculations show conclusively that the Hawking radiation is not a flow of positive energy from close to the horizon. It's instead a flow of positive energy starting around r equal 3m and negative energy flowing into the black hole near the horizon. So the way I think of it then is that it has more to do with the tidal disruption of vacuum fluctuations around r equal 3m. Part goes off to infinity with positive energy, and part goes into the black hole with negative energy, starting from a net zero energy fluctuation. And my arguments are in this archive posting at the bottom there. So I won't say more about this really, except that it does raise some question about whether Hawking radiation has really been done right. Now, but then arising from Hawking radiation is the notion of the information paradox. Now, Bekenstein and Hawking identified there's an entropy, a thermodynamic entropy associated with the black hole, which is proportional to its area, capital A, divided by 4 times the Planck constant. Now, normally in quantum theory, one's used to thinking of the thermodynamic entropy as being related to the total number of degrees of freedom of the black hole of the system, thermodynamic system, now in this case, the question is what are the thermodynamic degrees of freedom? And just those you can sort of think of as being localized on the horizon, in which case it's very natural that the number of degrees of freedom should be the area divided by the Planck constant. Or is it really the total number of degrees of freedom associated with the black hole, including those that have fallen into the black hole at some time in the past. And I have a definite. So this question has been behind what's called the information paradox, in that Hawking radiation radiates particles in the thermal state off to infinity, and that means they must be entangled if they started from a pure state, with some other quantum degrees of freedom, and so one has then a von Neumann entropy, which represents the total number of entangled degrees of freedom associated with the black hole, and the question is, can that become larger than the Bekenstein-Hawking entropy or not? Now, it's often been assumed that it can't, and the Bekenstein-Hawking entropy really is the total number of degrees of freedom, and that means that one's faced with a problem then of if the black hole, so these two entropies become equal at the page time, and which is when the black hole has lost about half its original mass, and if the black hole continues to evaporate, the area gets smaller, the entanglement entropy gets larger, one would think, and that would, violate this bound according to. And so people have all sorts of crazy, what I consider crazy ideas about how the quantum information doesn't really go into the black hole after all. Somehow it's either propagates just stored on the horizon, or is radiated at least, after the page time, that the particles that are radiated are entangled with earlier particles in the Hawking radiation. And that raises a whole number of issues associated with things like firewalls. And so this has been argued for over 40 years now. And still people don't agree on what the solution is. But, or is there some, drastic modification of the space-time near the horizon, which would prevent absorption of quantum information inside? And maybe there isn't a black hole horizon after all, and that one just has what some people call a gravistar or something, that there's somehow sort of something inside from just outside what would be the black hole horizon inside, which is very different from the standard Schwarzschild geometry. And so that point of view is still being pushed by a number of people, including Bob Holdham here in the physics department, and has ideas based on a particular formulation of quantum gravity, and Emil Motola has ideas about it too. So anyway, a number of people have speculated in that. I don't find those speculations terribly attractive myself. I find it very hard to believe that for a very large black hole, say a 10 to the 6 or 10 to the 9 solar mass black hole, that something peculiarly quantum mechanical happens right at the horizon, in which the gravitational and tidal forces are weaker than they are at the surface of the Earth for a very large black hole. So anyway, and the other point is that the whole idea of an event horizon, and this what really bugs me about a lot of the literature is that people seem to assume that just because classically there's an event horizon, and classically there's a singularity in the interior of the black hole, that when you take into account quantum field theory, you still have an event horizon, and the singularity, and and so they claim they have to do something drastic to prevent anything from going into the black hole. So anyway, I see no reason to suppose that's the case. And the energy conditions required for an event horizon and a singularity can be violated under certain circumstances in quantum field theory. And so why shouldn't the evolution of the black hole be different for that reason? Okay, so so what I'm going to talk about is the possibility that what happens in the interior of a black hole is that it evolves into a white hole. So instead of having trap surfaces, in which two surfaces on which all the causal, future-directed lines go to smaller radius, you have that evolves into a white hole where the reverse happens. Everything has to go out to larger radius, and then the white hole has a horizon which things can flow out of, and so if the quantum information flows out of the white hole horizon in some way, that could resolve the information problem. And if you started from a pure state, it could restore the pure state. So, okay, so what are my basic assumptions? Well, first off, I'm going to assume spherical symmetry, because it's much simpler than anything else. And units G equals C equal 1. I'm going to assume that quantum corrections are very small in the vicinity of the horizon, and in accord with this semi-classical calculation stress energy tensor. And then I'm going to consider the evolution of the geometry inside the black hole as a sort of a quasi-classical thing where you have a metric and a geometry, which you expect quantum fluctuations in the metric, but at least for a while, these should, so initially, I mean, it's not until you get down to a fairly small radius inside the social black hole that you would expect the quantum back reaction to be comparable to the curvature and modify the geometry in a significant way. Now that does happen at a certain point, and at that point, you should have a large quantum back reaction on the evolution of the geometry. But in this quasi-classical picture, you're saying that the quantum back reaction modifies the geometry, but in a fairly smooth way. In other words, the geometry continues to evolve with a different stress tensor than you would expect just from quasi-classical, semi-classical theory, which breaks down at that point. So you get large modifications in the geometry, but you can still argue that the fluctuations in the geometry are fairly small, because what's modifying the geometry is the total effect of a large number of quantum modes, and the fluctuations from any one mode should be fairly small in comparison with the total average effect. Now, of course, and then you've given a metric, and you can calculate an effective stress tensor just by calculating the Einstein tensor from the metric. And so that, in some sense, is representing, then the quantum back reaction. And one can ask, how reasonable, for a particular model, how reasonable that stress energy tensor is. Now, of course, when you get down to the Planck's length from the singularity, R equals to singularity, then any sort of quasi-classical picture really should break down at that point. You should have large quantum fluctuations, and it's not clear what you mean by an average geometry at that point. But I'm going to just go ahead and use the quasi-classical description, even in that very small radius. This is because I don't know how to do anything better than that. Now the quasi-classical, the quasi-classical evolution of the metric I'm going to assume does have there are calculations in loop quantum gravity which suggest a certain picture of how that might happen, and I'm going to follow that. So how do you then resolve the classical singularity at r equals 0? Well, I'm going to say in my model, which is, you can imagine other models, but is that you have the black hole being formed by some collapsing star or some collapsing shell. I'm going to assume quantum back reaction causes that to bounce fairly quickly in terms of local proper time. And so you have say a shell going in and coming back out again. And it doesn't spend a long time sort of with, Planck energy densities. Now, but outside the matter, well, you just have vacuum classically. I'm going to assume that the circumferential radius, in other words, the radius such that the area of the two spheres, 4 pi times the square of the circumferential radius, has a minimum value on a space-like hypersurface, which separates the interior of the black hole from the interior of the white hole. So it's that point that trap surfaces stop and anti-trap surfaces in the white hole start. And again, I'll describe a little bit about how this comes up. It's suggested, at least strongly suggested by loop quantum gravity. So this basic idea of the black hole turning into a white hole has a pretty long history of people speculating, but they haven't been terribly explicit about just how the transition happens. Either they just wave their hands and say, well, it's quantum tunneling from one geometry to another, which I don't find very satisfactory, or they consider what some people have considered as the case of a non-evaporating black hole, where you just take the crustal metric, in other words, the full extended Schwarzschild metric, which of course doesn't have any star, doesn't have a star collapsing in it necessarily, and in which the mass of the black hole stays constant in time and falls into a white hole with the same mass, and that is not very satisfactory because it's not solving because then you have a Cauchy horizon at the white hole horizon, and that's if you want to solve the information problem and restore unitarity, that doesn't really work.
So this is great. I love this partly because I'm thinking along the same lines, and there's an interesting issue about having a early universe bounce that would then automatically get into a quantum dominated regime. But the problem that, anyway, hoping to hear the solution to, is that the quantum diffusion forces are sort of spherically symmetric. They sort of go like scale, I think, to the -5, and it's not clear that they're strong enough to stop a collapse. And so what I'm looking forward to is that extra ingredient that would actually stop all the equations of state.
So what I'm talking about is not actually, so I don't claim to know exactly how the collapse of the star or the shell that formed the black hole, how that's reversed. That would, I think, definitely bring into these.
Well, yeah, I mean, the picture
But
It's actually, I think it's going to be intimately related, which makes this so much fun, is that the ideas of the universe is emergent. It's emergent from some kind of quantum fluctuation dominated regime. And the issue is, if you go to it from the other side, do you get into that regime? And then it's almost the same story that is being described here as the interior of the whole.
I have a more basic question. R equals A sits inside the Schwarzschild radius?
So article A, I'm saying there's some minimum radius A, which is presumably Planck scale.
Yes, okay.
And, okay, so this is the Penrose diagram of the sort of general picture that I'm considering. So here, between these advanced times, so here's past null infinity, and notice this structure of this Penrose diagram is exactly like Minkowski space-time. So there's no place for the quantum information to run and hide. So what you have then is, here you just have Minkowski space, this time. And then you have a shell coming in, say, and with some finite width, and this bounces and comes out again, okay? Now, so I'm not worrying, my model doesn't really deal with exactly how that happens. So my model is what happens outside the shell. And so we have here a black hole. So here, 45-degree lines are ingoing and outgoing radial null geodesics. And so the black hole horizon is this, well, from sort of here to here, is an outgoing radial null geodesic, which is actually, if the black hole is evaporating, it's actually gradually shrinking in radius. And the radius is decreasing, and that, and the black hole loses mass, right? So the radius of its horizon. And there's Hawking radiation going out just outside the. Now, the thing about Penrose diagrams is they can give you a nice picture of the cosmos structure, but they can be very misleading in terms of what's close to something else, because they're huge, can be enormous conformal distortions of the actual geometry. So the point is, in terms of the time it takes as measured at future null infinity here for the Hawking radiation to come out is just as long as the time it took for the black hole to evaporate, which is enormously long. It's m cubed over h bar, which for any known astrophysical black hole is huge numbers of orders of magnitude greater than the age of the universe. So it's just, now if there were primordial black holes, we started off with a small mass, maybe we could see something of this happening in the present universe. But for any black holes we know about, definitely not. Anyway, and then, as I said, there's then the Hawking partners are going into the black hole. Now, and then you have this space-like hypersurface at article A with a Planck scale length. And now, at this point, I'm saying that the evaporation of the black hole stops at some minimum mass, which is presumably Planck scale mass. And then you have the white hole. So the future of this transition radius, article A, you have R increasing and to the future, and you have this white hole region where all causal geodesics are outgoing, larger radius. And then you have the white hole horizon, which is the matter between where you have, so out here you have outgoing radial null geodesics going out to large radius off to functional infinity, but in here an outgoing Well, so the question then is, how does the quantum information that's coming across this article A surface get out to infinity? And that's be a subject of a good part of the talk. So, and then when the shell comes out, of course, then the idea is that this all, the Whitehall ends at that point, and you're just left with Minkowski space afterwards. Yeah.
Can I ask another dumb question? I thought inside the Schwarzschild radius becomes the time-like coordinate.
Right. So that's why article A is a space-like hypersurface, you see.
Okay, yeah.
Because it's a constant radius.
I want to think about a minimum radius.
And so changing radius means you're going in time, not in this region.
Yeah.
You're going, so a decreasing radius here is going forward in time,
Yes.
and an increasing radius here is going
Backward.
forward in time in the Whitehall. Okay, so this is, this is the overall hand-waving picture. Now, okay. Now, of course, what you have to address then is, what is it that imposes this minimum circumferential radius? Now, here I just quote there's a paper about a little over a year ago by Ashtekar, Omeda, and Singh. Don't claim to be an expert in loop quantum gravity, but these people are. And they claim that when they consider a fixed mass black hole, that they claim that that when you do calculation of loop quantum gravity, that you can think of what's happening at this minimum radius, that you get this kind of expression for how the radius varies in time. So this t here is sort of a time coordinate, where t goes from plus infinity on the black hole side to minus infinity to negative values on the white hole side. And it has this sort of funny looking structure. Now gamma, L naught, and delta C are standard sort of loop quantum gravity parameters. And now, first thing you can notice is that you can rewrite this rather messy looking expression in a very simple way. It's just r squared equals z squared plus a squared, where z is given in terms of their coordinate capital T by this expression, and a squared is just gamma L naught delta C times the mass of the black hole. Okay, so that's all this really is this kind of thing where there's circumferential radius squared has a minimum value at z equals 0, you see. Okay, and the way I've set this up is that z goes from minus, because I want z to go forward in time in the interior of the black hole and the white hole. The coordinate z goes from minus infinity, for outside the black hole, to plus infinity for outside the white hole, and is 0 at the horizon, at the transition, at the horizon. Okay, now, because I'm assuming spherical symmetry, that means you can write any spherically symmetric metric, given that the circumferential radius is c squared plus a squared, in this form where g, z, z, and e to the psi sub v are metric functions, which you have to specify if you want to make a particular model. And and you can use either advanced null coordinate v. So in the black hole, if you want coordinates that are regular in the black hole horizon, you want to use it at advanced time, because that's finite on the horizon, while the retarded time is infinite, on the black hole horizon. And then, but in the case of in the white hole, you really want to use a retarded null coordinate, because there the advanced coordinate is in advanced coordinates, the metric is singular on the white hole horizon. So to get something that's regular on the white hole horizon, you want to use retarded coded U, but the structure of the matrix is exactly the same. And with the signs I've chosen for this term, this means that both V and U increase to the future. So, of course, they're null coordinates, but the point is, if you take, say, an ingoing radial null geodesic, and you ask, take it and ask, you have a crossing outgoing radial null geodesic, and as you go from one ingoing radial null geodesic to the other, that V, increasing V, corresponds to increasing, so going to the future along the outgoing radial null geodesic.
So does, I don't know much about, I don't know anything about the loop quantum gravity constants that are entering here. How do they determine them? Is it?
Well, so that's what I'll come to next.
Oh, okay.
Okay, so in that Ashtekar et al. Paper, and this is other people who have looked at this make the same assumption, is they want to choose those parameters, loop gravity parameters, so that the minimum A is just when the curvature, which goes as m over a cubed, is of order 1 over h bar. Okay, that's just when the semi-classical approximation is really breaking down, and so they want to say that's stop, have then a sudden change from the black hole to the white hole at that point. Now, and that means that that A then depends on the mass of the black hole, because h bar is the fundamental constant, and so the smaller A. So this condition is satisfied. For a large black hole, it's A large compared to h bar, while as the black hole gets smaller, as it evaporates, the A would get smaller. So, and the point is, there's a basic parameter in loop quantum gravity which represents sort of they quantize little what they call plaquettes of area, and there's the minimum size of those plaquettes is, they assume, is something of order h bar, and is some parameter delta, which is they call the area gap parameter. So that's the really fundamental parameter of loop quantum gravity. These other things are not particularly, there are no preferred values in terms of the basic loop quantum gravity for the. So what they assume then is you choose gamma L naught delta C so that this condition is satisfied. But then A cannot be a constant for an evaporating black hole. So a black hole that's losing mass due to Hawking radiation does not have is losing mass, means that the A would vary, and then that makes it really hard to deal with what happens for an evaporating black hole. And
since the keyword area is used here, an area gap, area for black holes related to entropy, does it mean that it's like there's a spectrum with a discrete?
Yeah, so it could be interpreted in terms of some discretized spectrum of areas, or the area has quantum.
I don't believe this, but I'm going to say it anyway. It sounds to me like it's leaning towards a Bardeen. BCN Staff just joking, of course, but the gap does make you think that something interesting might be happening in terms of a.
Right. So that's. So what I'm going to assume now is that A squared in fact is a constant and is of order h bar. Okay. So it's the A squared is, I don't say it's equal necessarily, but just it's basically determined by this directly by this area gap parameter. Okay, and that seems much more reasonable to me. Okay, now then you're left, for a large black hole, then you're left with this regime between article A and when the curvature is becoming Planckian. And I'm just going to say that, well, the metric evolves in such a way that you can make the metric evolve in such a way that the curvature never does become super Planckian. It just sort of becomes Planckian and stays Planckian all from this radius here down to the Planck scale radius. Okay? You can do that by just choosing how the metric evolves in the right way, or how the metric depends on R, basically. So, and the point is, this is consistent with, this is not consistent with the metric being expandable in integer powers of h bar, which you might think would make sense in terms of quantum corrections to the geometry. And also suggests that m is perhaps should have a minimum value of order A, or in other words, of the order of the Planck scale at the end of the black hole evaporation. Okay, so that's, okay, so.
So, sorry to keep interrupting here. So A is setting a maximum curvature scale, and you can't go above a maximum curvature.
Well, so if you don't want the curvature to become greater than 1 over h bar, you have to do that by fudging the metric so that it doesn't happen. It doesn't happen automatically, and if you choose A squared as being
there was a
delta
period
squared.
when Werner Israel was trying to invoke a maximum to R, which was acting like a Hagedorn limit, so that R wouldn't get above this value, and he also was having, he didn't call them white holes, but it was an interior expansion into a de Sitter that could possibly occur.
Well, so that's another thing you can do. Well, I'm not going to assume
It's not
de Sitter.
related to that.
It's not particularly related.
To this. Okay.
Okay, so we have this general circular symmetric metric with these GZZ being, it's the inverse ZZ component of the metric. And that's related to this Misner-Sharp mass function, little m, by this expression. So this Misner-Sharp mass function is defined covariantly as the square of the gradient of the circumferential radius. That's the definition. And if you ask what that is in terms of GZC, it's just this. So it's something that's, you see, goes to 0, it's equals 0. And otherwise, you know, it's mainly determined by GZC. The Z squared over R squared goes to a constant once you get away from that transition region. All right, so so if you want to make a specific model, you have to dream up some particular forms for these GZZ and for this other metric function, psi sub s. And but the advantage of invoking this Schubner mass function is that the Einstein equations, so if you calculate the Einstein tensor, it turns out to depend on this mass function in a very simple way, in that the TVV is just related to the radial derivative of the mass function, and you get this expression. And TVZ, which actually turns out to be related to what's describing the flux of energy along ingoing radial geodesics. And on the black hole side, I'm assuming that is basically how the quantum information is transported inside the black holes along ingoing radial geodesics. And that's what they said, you see, is simply related to the time derivative of GCZ, but with the factor Z in front. So now if you assume the metric is regular, it requires that GZZ and psi sub v be regular functions, which means that this is saying then that this TVZ component is going to 0 as Z goes to 0. Now, in the black hole, it turns out that this is, you expect this to be positive because in the black hole, this TVZ is related to the energy flux. This was essentially minus the energy flux. And if you have an ingoing flow of negative energy that has a positive energy flux associated with it, because you have negative energy density and radial stress associated with it, but a positive energy flux. And so TVZ is positive, and you expect to be positive in the black hole and go to 0 at the transition. Now, this psi sub v, it turns out there's another component of the Einstein tensor, of the effective energy moment tensor, which T sub z super v, right, which is simply related to the derivative of this metric psi sub v. And given these three components, you can get everything else, semicircle symmetry. Then you have an identity which says that TZZ is given in terms of TVV and TZV. And then you have, there's one of the conservation of the stress energy tensor, which follows automatically from the Bianchi identities, gives you what this T theta theta, the transverse stress, is doing. Okay. So that's the. So what happens at the transition now? So we have trapped surfaces at Z less than 0. Okay, then I trapped it. Z greater than 0. Z equals 0 must be space-like. Now, for a space-like hypersurface, you have to have this GZZ, G inverse ZZ, at Z equals 0 to be less than, or, well, 0, basically, and equal to 0 only at the endpoint of the evaporation, which I'm going to define the advance time so that that's going to be at V, advance time equals 0. Okay. Now, okay, so that's, now the inflow of negative energy from the Hawking partners in the black hole, I'm going to assume goes to 0 at this endpoint, at V equals 0. And that, because it's proportional to the V derivative of GZZ, I'm going to assume that GZZ dV equals 0 at this endpoint, C equals V equals 0. Okay. Now let's consider the white hole. Well, as I said before, we really want to use retarded null coordinates in the white hole, just be able to have something that's non-singular at the white hole horizon. Now, so we want to switch to retarded coordinates. And this again is the retarded metric. And now U is defined, we can define U. Again, we've sort of assumed that V represents some sort of, advance time measured at infinity, at past null infinity. But I'm going to now define U so that U is equal to minus V at Z equals 0. So you have an ingoing radial no geodesic coming in through the black hole at Z at V less than 0, and then coming out. And when you consider the outgoing radial geodesic coming out of the white hole, that's at positive retarded time. which corresponds to that Penrose diagram I showed you before. And okay, so all this is just basically definitions. And you can then ask what is the transformation between the advanced null coordinates and the retarded null coordinates. And you find that GZZ just stays the same, and that that the psi sub u, either the psi is sort of a, think of it as a time dilation function. In other words, so psi being positive, either psi, well, so psi sub, so this E exponent should be small. If that's small inside the black hole, that corresponds to time running slowly inside in the deep interior of the black hole, which is what you would expect from gravitational time dilation. And but now at c equals 0, it turns out that these two things are equal from the way I define u in terms of v. And this dv du is, at constant c, is negative in the interior of the white hole, okay? And because it's just -1 by definition at c equals 0, we get this equality. Okay, so now how does the energy flow from the black hole to the white hole? And okay, so one way to look at that is to consider the physical components of the stress energy by projecting it onto an orthonormal frame. So, instead of coordinate components, you want to talk about components in a local Lorentz frame, okay? Now, an obvious choice of frame at c equals 0 or near c equals 0 is to make the radial basis vector, there's the space-like vector, it's pointed along the z equal constant hypersurface, because all z is essentially r. R is a time coordinate here, it's not a spatial coordinate. So, okay, so at the z equals 0 hypersurface, if the collapsing star is off to the left here, then we're going to say the outgoing, what I call the outgoing radial direction, is pointed at constant z, in other words, at constant time, along the transition hypersurface. And then the time component of the tetrad is pointed orthogonal to that in the future direction, okay?
So can I just go back to Z and R and A and all of that? So we have Z equals 0 being what's considered to be the boundary between black hole, white hole transition. But then R, in both cases, would be A. So is one envisaging that there's this kind of
right? So R is continuous
yeah.
across the transition. You really should think of it as being sort of fuzzy in that region because of the fluctuations in the metric.
So that's the picture that you have the black hole, you're trying to make a singularity, but instead quantum effects become dominant.
Right.
It creates this little ball, and then there's another side of the ball, which is where
the two spheres shrinks down in the black hole,
yeah.
But then because of quantum effects, it stops shrinking and starts expanding as you go into the white hole.
Great.
Right.
And yeah, okay, good, got it.
Okay, so now you can express the energy density E, the energy flux F, and the radial stress B sub r in terms of the coordinate components that we talked about previously. And in advanced coordinate components, we get this. And notice that F goes as, since remember GZZ is negative here because Z is a time coordinate, not a spatial coordinate. So GZZ is negative, so this minus GZZ is positive. And so that F has the same sign as dVz as I claimed earlier, because there's a minus sign here. And then, and there's associated with a positive energy flux, there's a negative energy density, right? From here, now of course you also have this minus TZZ term, but in terms of what's directly associated with the flow of energy, it's basically as long as it's along ingoing radial energy geodesics, it's basically determined by TVC. And then the radial stress is also negative if F is positive. Right? So that corresponds to locally then to a flow of energy going inward. Now, in retarded coordinates, there's a flip in the sign here on F. So in retarded coordinates, which we're using in the white hole, now F goes to 0 as linearity in Z, just as dVz does at the transition. So you expect F to change sign and become, if it's positive in the black hole, it should become negative in the white hole. Okay. Now, if the flow in the white holes is a constant retarded time, then TUZ is going to represent the flow along. But now F, of course, is not going to change. It's something non-zero in the black hole. It's going to stay the same, at least for some time, going into the white hole. So here you see you have, now so in the white hole, F should be negative, right? And a negative F, given these signs, corresponds to a negative E, energy density, and that gives you an outflow of negative energy, right?
Can one think of, I mean, this is a little bit like a continuity relationship across this.
So here's the some things behave smoothly across.
Can we think of this in terms of something like shocking behavior with the stress energy continuity, where you don't have to say the details of what the form of that stress energy is, it's just something?
Well, I'm basically assuming the form should be some smooth function, not analytic necessarily, but some smooth function across the transition.
I mean in terms of particle content.
But it could behave quite differently once you get away from the transition in the white hole than in the black hole. Okay, so okay, so if the flow of energy is along ingoing radial energy geodesics in the black hole and outgoing radial energy geodesics in the white hole, what you get in the white hole is an outflow of negative energy. All right, and across the white hole horizon. And this is just saying all that. Now, on the other hand, if in the white hole you assume the flow stays along ingoing radial energy geodesics, so that's not, it's the Hawking partners then are not coming out of the white hole. They're going along ingoing radial energy geodesics. Then, well, you would say, in terms of the slope of frame, is that you have an inflow of positive energy. Now, that may seem sort of strange because you want dm, the Schwarzschild mass function, to be decreasing as you go further away from the collapsing shell on both sides, right? Now, what's happening then for an ingoing radial geodesic in the white hole is that, well, you can have a local positive energy density, but it corresponds to m decreasing with advanced time increasing. And so basically what's happening is that the ingoing radial geodesic, once you get into the white hole, corresponds to, if you think of it as a geodesic, it's a geodesic whose energy in the local frame, it has a negative killing, killing energy. In other words, relative to infinity, a positive, say, energy photon going along the singular real geodesic in a white hole is actually contributes negatively to m, the mass function. And okay. So now, so as little as I need, I'm not going to assume very much about how these GZC and either psi v and psi u and so on, how they really vary over the whole space-time. I'm just considering what happens near the transition. So the other transition, though, from the conditions I've imposed on how GZC has to behave near the transition, you can say that this should be the form in advanced coordinates of GZC. So you have minus, and capital A and capital B are sort of positive, some positive constants of order unity, basically. So it says then that z equals 0, GZC is negative, which is what you want. And it says that GZC dV goes to 0 as v goes to 0. And then you expect GZC to increase away, at least, well, certainly on the black hole side, to increase away from this, going back into the black hole. And now for this psi sub v, you can use your freedom. You can change your scaling of the advanced time, say, if you're working in advanced coordinates, to be such that this psi v is 0 if z equals 0. I mean, it's just, it's a gauge choice. It has no physical meaning. And then but you expect it to increase going away from z equals 0 because you expect this, again, this is, either psi v should have a minimum in the deep interior of the black hole as opposed to what happens further out. So all three constants then are, A, B, and C should be some positive constants of order unity. And now in the white hole side, all we have to do, and GZC is the same, so we just change v to u by saying v is equal to minus u, but that just means that we just replace v by u there since it's squared. Okay, so, and then now we have from the metric, from the GZZ, we can now just calculate what this effective stress tensor is. And it turns out to have this form. Just the TVZ is positive for v less than 0 and z less than 0 on the black hole side, and the white hole side you have u greater than 0 and z greater than 0. So again, TUZ is positive. Of course it's 0 right at the transition, but as you go away from the transition on either side, both are positive. Now. Everything's finite. I mean, the main takeaway of this is that everything's perfectly finite at the transition and at the endpoint. There's no singularity at the endpoint. And okay, now okay, so now. So the black hole horizon is this hypersurface, and from the form of which you can calculate initially as you go away from z equals 0 goes as a v cubed, z goes as a v cubed over 6a squared in the black hole. So that's the black hole horizon, and remember v is negatives, and so this is. When you're in the black hole, so this z sub h is negative. And then there's an apparent horizon, which is just, you see AH goes this square root times the advanced time, again, which is negative on the black hole side. And, but because TUZ is positive, we already said that that means that there's a flow of negative energy across the white hole horizon. So in saying that is that initially there has to be a flow of negative energy across the white hole horizon, as long as we're close to the beginning of the white hole and end of the black hole. So so there has to be negative energy going off to infinity, at least for some limited range of Planck scale range of retarded times, which.
So can I just ask? So I have an evaporating particle out here. Then the picture is, which I wasn't sure if you were saying you didn't like this or not, that we have a partner that's going.
So you have a partner which has, you really shouldn't think of it as a particle because it's carrying negative energy.
Right, exactly. But it's correlated, that is to say.
Right, it's correlated with the outgoing.
And so then what's
positive
happening is that in spite of the fact that whatever that bit of information is may transform itself in terms of particle content, the idea is that there's continuity of that sort of energy thing as you go through this
Right.
region. And then what comes out the other side is the expression of the entanglement. That is to say, the entanglement is on the other side.
Right, so you have this negative energy coming out, which is tangled with positive energy. It came out of the black hole much earlier, much earlier.
Right, so we're entangled with the black hole that we came out of at the beginning of the universe. Is that the...
Well, no.
That was it.
Okay, so now we can consider alternatives for how the white hole should evolve. We said initially there's negative energy going off to infinity, but it doesn't have to stay that way. Now, if you assume it does stay that way, so you just have this stuff coming in along ingoing radial geodesics and going out along outgoing radial geodesics, then what happens is the mass of the white hole steadily increases until you get to when the shell that formed it, everything, comes out. At that point, the mass of the white hole is just essentially the same as the mass of the original mass of the black hole when it was just first formed. And so the positive energy. Now there's a problem with this, and that is that when you have negative energy going off to future null infinity, which is asymptotically flat, I'm assuming, for a very long time, which is the lifetime of the white hole should be roughly the same as the lifetime in the black hole. Everything is just the time reverse in this scenario one. That violates theorems proved in Minkowski spacetime. Of course, there's locally Minkowski spacetime, future null infinity, which says there's the minimum average energy. When you average the energy density as measured by a freely falling time-like observer over a long time, there's a minimum energy, which the longer the time you average, the less negative it can be. It can be negative, but it can't, how much negative it can be gets smaller and smaller the longer the time you average. And the problem is that in this picture, the negative energy that's associated with this outflowing Hawking partners is too big, too negative rather, to be consistent with this asymptotic Minkowski space picture. So you might worry about that. You might also say, well, the global space-time is not at all Minkowski. And so maybe these theorems don't apply, but you can certainly worry about it. Now, the other thing you can say is that the outflow of negative energy across the white hole apparent horizon stops after, something Planck, after some Planck scale time. So TUZ just goes to 0 at the white hole horizon, which is, again, is at GZZ equals 0. While the white hole then still has a Planck scale mass. Now, if that happens, then you're just freezing the mass and the radius of the white hole to be, at that value when TUZ goes to 0, until something happens, so you're saying, then that's just going to be frozen until the shell of matter comes out. Okay? And so most of the quantum information and negative energy of the Hawking partners is still trapped inside the white hole until matter comes out. And well, there are then issues there too, perhaps less serious ones, but no.
In that case, you're still evaporating, and so
well,
what happened at the end?
Well, so the black hole evaporates up till V equals 0, right? Which is this white hole horizon. And then, so what I'm saying then is the white hole, after an initial period of anti-evaporating, just stays frozen. And so, so everything, the quantum information is still trapped, okay? Most of it. Some of it presumably got out in that initial burst of negative energy. And now, in scenario 1, the end of the white hole is there's really no problem. The problem is what happens along the way. But at the end, you just have this massive white hole, and the shell comes out and takes away all of that mass off to infinity, and so you don't have anything left, and it's just the Gaussian spacetime again. Okay, now scenario 2, things are more complicated. So we said the Hawking partners and the quantum information are trapped inside the white hole. And the only way I can do that is to be going along ingoing radial geodesics. If there's anything that deviates significantly from an ingoing radial geodesic, will go across the horizon, which he's saying isn't happening. So, and the rays of the horizon is frozen at some, and the mass of the white hole is frozen at some value m1, which is, larger than the final mass of the black hole, but not a whole lot larger. All right, so now, because we've gone across the transition, this flow of, say, call it flow of negative energy, but locally in the local frame, it's actually positive energy density. But its contribution to the Schwarzschild mass function is negative. And so then, and it converges, ingoing radial geodesics as you go along, propagate inside the white hole, get closer and closer, in a certain sense, to the white hole horizon. They sort of asymptotically approach. And there's also an exponential blue shift as measured by some free fall frame at the white hole horizon. Now, so whatever you end up with it then is a sort of a shell of stuff going just barely inside the white hole horizon at this radius r1. And then you have the outgoing matter, which I'm going to assume you can think of as just a radial outflowing shell of initially positive energy. And So what that means, and so this, so you have this sort of collision of these two null shells. And so Dre and Hooft, a while ago, worked out that you can use sort of local conservation laws to constrain what this final mass M2 is. We said we have this mass M1 a few times the Planck scale, M naught, because if we assume everything in the collapsing matter is coming out here, it shouldn't leave anything behind, and so you just should have empty Minkowski space-time here. And that means this mass should be roughly the original mass of the black hole, which is really for a initially large black hole, much, usually large compared to M1. And under those conditions, what you get for M2 is, and R naught is just the circumferential radius at the collision point. And R naught is going to be, just slightly less than M1, 2M1. And so what you end up with is 2M2 is, because this epsilon is something very small, and R naught over 2M naught is very, very small. This 2M2 is essentially the same as, M2 is essentially the same as M1, just very slightly less, infinitesimally less. Now that means you have an ingoing shell with a positive mass, right? Because 0 inside. And these, you assume these are just Schwarzschild geometries here. And so you have a positive mass shell going in. Well, that's going to form a black hole, right? And it's already on the verge of, essentially on the verge of forming a black hole right from the beginning. But it's a Planck scale black hole. And now you could say, well, that should evaporate, that black hole should evaporate quickly in a, an order of Planck time. And then turn into a white hole again. But now a very, a white hole without, which, if it evaporates for a short time, perhaps could completely evaporate. It's, in other words, so you have positive energy going out from the black hole here, but then the black hole turns into a white hole again. And you have negative energy coming out of the white hole, and you end up with a net balance. Well, so it's a little unclear what happens to the white hole, that final white hole. But anyway, so the idea then is that now this is a much more complicated scenario, but and it's also less solidly established. And okay, now I just want to say a few words about entropy before I wrap up. And so, as we said, the von Neumann entropy, or the entanglement entropy of the black hole, steadily increases as the black hole evaporates. And the horizon area of the black hole steadily shrinks as it loses energy, loses mass. And so there's this crossing point at the page, what's called the page time. And when the black hole's only lost about half its original mass. Now, but I'm assuming the black hole keeps evaporating past that point. So the von Neumann entropy is going to become huge compared to so the Bekenstein-Hawking entropy is going to down to the Planck scale, and the entanglement entropy is going up to something very large. All right. Now, I'm saying that in this, at least certainly in this picture, that it makes no sense at all to say that the Bekenstein-Hawking entropy is a measure of the total number of quantum degrees of freedom in the white hole, in the black hole rather. As you can see by looking at and so at the end of the black hole, the von Neumann entropy is some hugely larger than the Hawking energy. Now you can see why that's. But if you say that you have the Hawking partners flowing in like this, when they cross into the white hole, they're a very large space-like separation from the end of the black hole. And to say that the black hole at the end here is in any kind of thermal configuration is crazy. You know, instead you have, so that's saying then that you should just think of the Beck's-Steiner entropy as being some sort of surface states corresponding to surface states in the black hole, not on the total entanglement entropy.
So we've been conditioned to think that you can't really store more than one bit in a Planck volume cube.
Right. Okay, that's the next point. Okay, so let's consider then the volume of this space-like hypersurface at z = 0, right? So it's this sort of long cylindrical, I mean, you know, it's a cross-section area, which is just 4 pi a squared, but then it goes on for an enormous proper distance because, you know, of course, you know, there's, well, aside from this factor of either psi v, you know, the range of advanced time is usually long, right? And so you have then, in advanced time d little v, you have a volume at this minimum hypersurface, just given by this, and you can estimate how many quantum degrees of freedom are crossing that spatial region in terms of the luminosity, Hawking luminosity, and the Hawking temperature, saying that the average energy of, you can count the number of Hawking particles going off to infinity, roughly taking the per unit advanced time by going take the ratio of L sub h to T sub h. And that turns out to then be, so the number crossing is dV over m. And if you assume that this time dilation, either psi v, goes to something like a over m, well, if it's just constant at 1, then of course it's even more, you know, even better. But it can be as large as something going as, you know, be small of order a over m, which reduces the length of that long cylindrical spatial surface. And it turns out that the number per unit volume is just h bar over a squared to the 3 halves. And if a squared is a bit, you know, larger than h bar, I mean, you know, there are factors of order unity here, but it's at least certainly plausible that there's no need for more than 1 per Planck volume, 1 degree of freedom per Planck volume. Okay, so.
Geometry is very different than a classical black hole.
Right. And I think so the final slide here is just that summing this up. Now, one thing that quantum information, we said that in this second scenario that everything is trapped inside the white hole. Now, it's conceivable that the quantum information that's trapped could leak out gradually, as long as it does so without carrying negative energy to infinity. So you could imagine having vacuum correlations, you know, vacuum fluctuations near the white hole horizon, which flow across, which have 0 energy, but carry quantum information. And, you know, whether that's, I've heard very reputable people come off on opposite sides of that question. But, you know, I think it's not implausible. Anyway, so this is all, of course, just a conjecture, and haven't proven anything except that if you believe the loop quantum gravity stuff, then at least it seems to justify something vaguely, at least vaguely like this. Okay, well, thanks. Yeah.
So I'm wondering, how stable are these solutions to angular perturbations?
Unstable.
How stable are these solutions to angular perturbations, right? Because if anything is incorrect, you assume that everything is spherically symmetric.
Oh, well, of course, black holes aren't in general spherically symmetric. And the horizon, the singularity structure, the horizon structure inside the black hole is in a rotating Kerr hole is quite different from the Schwarzschild. So that's something I haven't really, can't say I've really figured out exactly what should happen now. Now, one possibility is that if the black hole, as it radiates, Hawking radiation, spins down, it's possible by the time it gets down to the Planck scale, it's at least to a good approximation of Schwarzschild black hole. But again, that's and I think it's possible that would happen, but whether it would really make the Schwarzschild metric a good approximation at the end, I'm not sure. But so that is certainly an open question: is how do you deal with?
But that might not work against you at all. In fact, it might help the cause. If one thinks of BLK, which has all sorts of arbitrary anisotropic stresses which are operating, presumably that will be an aid to quantum effects becoming sort of even more significant.
So,
Might be, but not be. The thing that I had a problem with is that nominally that goes like scale factor to the -6 compared to what I was saying, that naive quantum fluctuations are a to the -5, and it's hard for you to defeat that. But here, the key ingredient is to do this quantization, which gives you maybe a fixed day. I mean, what does Ashtekar say about you fixing A whereas he doesn't?
Well, I haven't heard directly from him. I haven't heard violent. So, well, you know, he's basically assigned one of his postdocs to correspond with me. And the postdoc didn't raise any violent objections to that. That's all I can say. But, so, and he had other kinds of objections, which I don't think were that serious. But anyway. So, yeah, so, and the point is, the nature of the quantum back interaction could be quite different inside, say, a Kerr black hole than, at least in terms of what happens to the, you know, the horizons in the Kerr black hole, but in the interior of the Kerr black hole. But it could also, you know, completely change the whole geometry of the interior of the black hole.
Exactly. I mean,
So who knows?
what you're doing is saying that you can marginalize over the high frequency fluctuations to get a mean geometry, which is what you're using for GZZ and all of that, and it could be quite, you know, quite modified as you get down towards the Planck, for sure. Right? So there's many possibilities, but it's a fascinating class of ideas, I think.
We're a bit over time here, so I'm going to suggest we continue the discussion upstairs over cookies.
Okay.
And we can thank the speaker again.
No, sorry.
Oh, it's fun, really fun. And not the least of which is that, although I'm not nearly as advanced as this, I had been thinking along somewhat the same line, because we have this issue of, well, it's like the inverse of the emergence issue. Right? It's what happens, and so that there would be a quantum fluctuation dominated regime, and then you would be emerging from that, which I guess you could say has some characteristics of a white hole. And then if you wanted to say the Turok Steinhardt thing, you probably would, well, the way I would see it is maybe you collapse, but then it's quite possible you could get into a quantum fluctuation dominated regime, which loses a lot of memory of the whole. I like the possibility that we have entanglement across the boundary, though. That's really quite a fun idea.
So Neil nowadays is pushing something quite different as far as he's saying, let's say that if you take the radiation-dominated Robertson-Walker geometry, right? If you do a conformal transformation to get rid of the scale factor, then you can have a CPT invariant universe in which basically the singularity, so you have the full range of, so everything happens, in a time-symmetric way, but a local observer would have, on both sides of the singular time, at the zero conformal time, that the observer would interpret that he has an expanding universe with essentially the same properties. So anyway, it's an amusing idea. I don't know. So it's not that,
history to that too.
so that not you have some,
But there's history to that too.
so it's not that you have some